Hey guys, this is Sarang from Skill-Lync. First of all, thank you so much for being part of this course and I hope you're really enjoying it. In order to consistently improve the quality of the course content, we like to conduct surveys so that we can get critical feedback from our users. A link to such a feedback form is provided down below. Please take the time and fill it. And be as critical as possible because your valuable feedback helps Skill-Lync better its courses. I once again thank you for joining this course and I hope you finish it successfully. Bye.
Welcome back to the demo on Chapter 10. You will start this tutorial with the partially built model. The points, bodies, graphics, and the joints are created for you already. So you need to create the curves and the curve-to-curve constraint. So let's get started. So let's open the file from model files that are available. So go to Chapter 10 and you have the cam follower constraint start.mdl. So double click on this and this imports the model. So you'll be getting one more assignment in this particular chapter, wherein you'll be asked to replicate this model and basically to build this model from scratch. Okay, I'm using this partially built model in order to save time, but you guys will be doing this particular demo. You'll be practicing it once I'll be showing it to you by building this model from scratch. So before we get into the further model building, let's explore what all this model already contains. So it has 4 bodies. One is the default ground body, and then you have a cam, so which is this particular green graphic that you can see, and then you have a follower shaft, which is this rectangular piece, and the body, the center of mass is right here, which is, as you can see, it is highlighted on the screen, and then you have the follower roller, which is at this location. So these are the different bodies that are used, and you have these are the various graphics that are used. The graphic for the cam, the graphic for this follower shaft, the follower roller, and some other small graphics like this is the cam pivot graphic. So you have another bolt that goes inside, which is represented by another graphic. So that's another cam pivot graphic, and then the roller pivot graphic, and the one inside the cylinder which is inside that, so that's the second graphic, and then this follower translational joint. Okay, so these are the different graphics that are used to create this model. Okay, and now let's see the joints that are used to create this model. Okay, we have the cam pivot joint here, which is a revolute joint, so which allows the cam to rotate along one particular axis. Okay, and then we have the follower translational joint here, so which allows the reciprocative motion of this follower, and we have the follower roller joint here. So this roller is allowed to roll along surface of this cam. Okay, so here we define a ball joint. So here we have a revolute joint, and then we have a translational joint here, and here we have a ball joint. Okay, so 3 different types of joints that are used here, and we have just the one marker, which is the global reference frame, and we are using many hard points to create these bodies. So this is the overview of the model, of the partially built model. Now we'll continue building it further and try to simulate the curve-to-curve joint. So now let's start by adding curves for the cam profile. So we can directly go to the toolbar here, right click to create the curve. So let's start by giving meaningful names. So let's call this cam profile. So once you've given a meaningful name to it, say OK. So then you come to the curves panel. So in the curves panel, you need to create a 2D spline now. Okay, so from the properties tab, you can go to the file, the open folder option or the icon in the panel. So it comes to your working directory, and you have a file called as camprofile.csv here. Okay, try to load in this, say open. Okay, it's got imported. So now you'll have to do a couple of things here. So change, so this cam profile, let's go ahead and open this in Excel and see what it looks like. Okay, so as you can see, it has 3 columns. Okay, so it is a 3D spline and not a 2D spline. So let's go back. We've already imported the spline here. So here from 2D Cartesian, you can change it to 3D Cartesian. Okay, so now you have X, Y, and Z, and this option from open curve, change it to closed curve. So once you do this, you can keep for the X radio button, you can keep block 1 and column 1. And for the Y radio button, you can choose block 1 but column 2. And for the Z direction, try to load in the same model, same CSV file, and you can go to column 3. So we have X values that will be taken from column 1 from this particular Excel file. Y values will be taken from column 2 from this Excel file. And then the Z values will be taken from column 3 from this particular Excel file. Okay, so this is your CAM profile. So you got a 3D spline for this CAM profile. Okay, so now let's create a follower profile. For that, let's create another curve. Right click on this and give meaningful names to it. Call this follower roller profile. Say okay. So here we want to enter it as an expression, so or a math function. So first you change this from 2D Cartesian to 3D Cartesian. Okay, once you do that, you'll be selecting from for the X radio button, you'll be selecting math. Okay, and then you start typing in your function here. Okay, so you can go in between these curly braces and start typing 5 times sine into 2 pi times, then you have to give the time interval. So 0 is to 1 is to 0.01. So close 2 braces here, and then you have the curly braces after that. So just click on this evaluated to see. Okay, it says error evaluating. So there's something that we've added extra while adding the braces. Okay, so here we need to open the parenthesis here. So we have 3 parentheses open and we're closing 3. Okay, so this should be right. Let's go to evaluate it and check if the expression is right. Yes, perfect. So you got math function for the X values. Okay, so what this expression does is, let me go back to the function builder. So the expression that you've given here, it will create an array of points from 0 to 1 in the increments of 0.01. Okay, that's what it means. So, so 0 is to 1 refers, it has to create the array of points from 0 to 1 in the intervals of 0.01 or in the increments of 0.01. So that's what it will do. Okay, and that is multiplied by 2 pi times 5 times the sign of this value is multiplied by 5. So that's what this expression is about. And now let's go to the y values. Again, I want it to be a math function. So I'll go here, go to the expression builder. So here, let me give a cos function. So 5 times cos of 2 times pi times 0 from 0 to 1 in the increments of 0.01. So this should be right. And create a similar expression for the z direction from 0 to 1 in terms of 0.01. Okay, so now I'll basically explain why I'm trying to do this. So when I define this CAM profile curve in the z direction, if you go and open the file, you can see that the third column is all zeros. Similarly, if I go to the follower profile, it's again the third column is all zeros. So I'm basically doing this to give you an example how we can work with the 3D splines as well. Okay, so but in reality these two curves will be 2D splines. So the CAM profile and the roller profile will be 2D splines. So I'm just trying to give the 3D Cartesian and using the z values, but I'm giving all zeros there. So just so that when you have an application wherein you have to specify the third column, you know how to do it. Okay, that's the reason I'm doing this. We'll be changing this option from open curve to closed curve. Okay, so now both of them have the curves defined. That is the CAM profile as well as the roller profile. We have for CAM profile, we have it from an Excel document. And for the roller profile, we have it from the math functions. So now what we'll try to do is set up a CV constraint between these two curves. Okay. So first, let's start creating markers for that. So go to this option. This is to create markers. Right click. So you can give the name as cam marker, and variable name also you can mention it as cam marker. So here you need to select the parent body, the origin, and you want and the axis along which you'll be aligning it. So go to the parent body here, double click on this body option, and for the origin point, the point at which this marker has to be placed, you need to select the pivot point. Now for the axis, you can just accept the defaults and you can start adding one more marker. So right click and you add a second marker. That's basically a follower marker. So if you start giving meaningful names for each of the entities that you create, it will be really helpful if you face an issue later during the model building process. If you get an error or something, then you can just go back. If you've given them meaningful names, then you can go back to the exact same location and do the corresponding changes. So try to make this as an habit to give meaningful names for, especially when your simulation or the model is going to be a little bit complex. So call this as follower marker, the variable name. And I also want to remind this in case you have forgotten that the variable name can only be changed at the time when you're creating a particular entity. It cannot be changed during the model building process, whereas the label name can be changed anytime during the model building process. Okay, so say okay, and here you'll be selecting the follower as a parent body. You'll be selecting the follower roller, and the origin you'll be selecting the follower revolute joint, that is this particular. So you can see that a marker gets created at this location on the roller and at this location for the. So now what all we have done is we have created the two curves, we've created the markers, and now it's a time to create the CVCV joint. So now we need to know where the CVCV joint is located. So if we go to this joints option and right click, and if you just see it in the drop down menu, you can notice that the CVCV joint is not in this location. So these options that you can see here are related to your constraints. Okay, so these are the icons that are related to your constraint. So this particular icon that you can see in the end, okay, is labeled as advanced joint. So this particular joint, CVCV joint, it comes under advanced joints. So you need to go there. Okay, so you can give a label name as CVCV. In here CVCV, and you can go to this location and select curve to curve and then say okay. So it brings up the curve to curve joint panel. So you'll be in the connectivity tab. So in the connectivity tab, you need to select the curve. Okay, so curve 1, double click on this and select cam profile and say okay. So you can see that this trajectory is created. Okay, and go to curve 2 and select the follower roller profile as curve 2 and say okay. After you define the two curves, you're supposed to give the reference markers. Okay, so the reference marker 1 will be the cam marker and the reference marker 2 will be the follower marker. So now you can see that a trajectory of the path is created here and on the roller as well as on the cam. Now let's specify the cam motion. Okay, so for this, let's go to the model browser. Let's add a constraint. So right click, add a constraint. That's nothing but the motion constraint. Okay, so let's call this cam motion. Cam motion. So even here you can give cam motion. Okay, and say okay. So in the connectivity tab, let it be defined on the joint itself. Okay, so you double click on the joint and then you want this motion to be placed at the location of this cam pivot joint. Say okay. So this will apply the motion to this particular revolute joint here. Okay, and this default type is a displacement rotation. So here you can see that it is taken as displacement. So go to the properties tab here and let's try to give an expression for this motion. In the last exercise, we had given the motion as a curve, but here we'll be defining the motion as an expression. So a very simple expression. Let's go to the function builder expression. Let's go to the expression builder and then just give 10 times the simulation time. Okay. So once this is done, there's one more important thing that we got to do in this particular simulation, wherein we need to specify the gravity. That's because since the shaft is along the y-axis, we want to give the gravity to be in the negative y direction. Okay, so in order to specify that, let's go to gravity. So if you expand this miscellaneous and if you expand forms, you can find gravity. So click on this and go to the y component here and give minus 9810. So this will be in mm per second square. So once you do this, you need to specify the output request. Okay, so what we want to do here, we want to basically monitor the reaction on this CV-CV joint that we have created. Okay, since it can help us to verify the correctness of our results. So we've established the CV-CV joint, but now we want to get the reaction at the CV-CV joint. Okay, so by the end of this demo, I'll discuss in detail about the lift-offs of this particular cam follower mechanism. So now let's go ahead and apply this particular output request so that we can monitor our CV-CV joint. Okay, the reaction on our CV-CV joint. So to add a output request, you can either go to file, you can either go to model, right click on the model, add general MDL entity, and you can go to the output, or you can directly go to this option and right click and you can add the output request. Okay, so you give a label name here called CV-CV reaction. Okay, so CV-CV reaction and say okay. So change this option from displacement to expressions, and in the F2 expression box, go to the expression builder and specify an expression. Let's go to the force tab and click on CV-CV. And the CV-CV joint, basically it has 4 arguments. So the first argument is the ID, second argument is the J flag. Okay, if it is 0, it gives the reaction on the I marker and 1 on the J marker. Okay, so if this particular the first one is the ID of the CV-CV joint, the second argument is basically the J flag. So if you give if you basically mention 0 in the second argument, it gives the reaction of on I marker, and if you give 1 in the second argument, it gives a reaction on the J marker. And this is the component of reaction, the third argument, and the fourth argument is basically the reference marker. Okay, if it is 0, then it implies the global reference frame. Okay, so let's try to give that. So go to the first argument. In that, go to properties. So let's try to give the CV-CV joints ID. So joint, so it should be under advanced joints, not joint. So let's go to advanced joint, CV-CV joint, and its ID string. Say add. So we got the ID string of that, and here we will specify the J component or the J flag to be 1. So we want the reaction on the J marker. And then here we'll give it as 2. So this is the component of reaction force. And then the last option we'll specify as 0. So we want it to be in the global reference frame. So let's see if this is right. Okay, so there are no errors. This is the right expression. Okay, so now what we'll try to do is go ahead and start running the model. So go to the run option here, and we need to change certain things. For example, the end time, we can increase it to like 6.28 seconds because I've run the simulation before. I know exactly what end time I need to give, or the simulation time I need to specify. And the print interval, we can leave it as it is. But then let's go to this tab here, which is called as the simulation settings. And here, let's go to the transient tab, which is the second tab. And here, change the DA index from 3 to, so when you change the DA index from 3 to 1, So this DA index 1, it adds system velocities to the error control, okay, which will generally compute a more accurate answer for the same integration tolerance setting as 3. So it is DA index should be set to 1 if you're trying to, if your system has a lot of velocities involved in it and you want to monitor that. So it adds the system velocities to the error control. So you need to change the parameter from or the value from 3 to 1. So once you do that, say close. So you can try to save this as camp follower constraint .xml. So let's go to animate and see if our animation looks right. Okay, so this launches hyperview in the second window. So the simulation looks good. Okay, so let's come back to motion view. Let me stop this animation. Come back to motion view. Now we want to plot some graphs. So go to plot. This will launch hypergraph. So here you try to plot, go to in the y type, go to body. So after going to body, go to the follower shaft and its displacement in the y direction. The displacement of this particular shaft, which is having this reciprocating motion in the y direction with respect to the ground. So say apply. So this is what you're expecting. So the maximum displacement of this shaft that you're seeing, the follower shaft, will be 25 mm, okay, at the peak position. Okay, so I hope it's clear. Okay, and there's one note that I have to mention here. So this is basically regarding the liftoff. Okay, so in a real physical world, the dynamics, it causes the follower to lose contact with the cam. Okay, so this is something that we've modeled in virtually, but if you take actual scenario, okay, so there will be some cases when because of the dynamic forces, the roller follower that you have, it can lose contact with the cam. Okay, so this particular thing is called liftoff. Okay, in such cases, modeling the system using the CVCV joint will give us totally incorrect results, because in CVCV joint, it basically constrains the follower point to be always on the curve. Okay, so if you want to simulate such cases wherein you wanted to model it close to the reality, then you need to use force-based simulation. In the sense, you need to set up a 3D contact between the cam and the follower, and then you're supposed to measure its output. Okay, so to see if there is any liftoff or not. But this is a quick way of simulation, and it takes very less time for doing this. But if you want to set up a 3D contact between the follower, the roller follower, as well as the cam, then it is going to involve some complexities, and also it's going to take a longer time to run. But that is more closer to the physical world compared to this. So that's one note I wanted to make. So at the end of the next chapter, which will be on the 3D contacts, you can try to use the same model and try setting up a 3D contact between the cam and the follower, and try to simulate the model and see what results you get. So this brings you to the end of chapter 10 demo. Thank you.